Semigroups and their representations, Lecture 5, Problem Session. Problem 1. For a positive integer n, let Dn be the set of all elements alpha in the full transformation semigroup Tn, which satisfy the following condition. For any element I in our underlying set 1, 2, all the way up to n, alpha of I is less than or equal to I. Prove that Dn is a sub-semigroup of Tn. This is usually called the semigroup of order decreasing transformations, because if we have a transformation from this semigroup and we apply it to an element, we get the same element or something smaller with respect to the natural order. Determine the cardinality of Dn, and describe the idempotence of Dn and determine their number in terms of some standard combinatorial objects. Solution. Let us take two elements alpha and beta in Dn. So we have two order decreasing transformations. Let I be some element in our set n underlined. So this is the set 1, 2, and so on, all the way up to n. So using the definition of Dn, we have that the composition of alpha and beta applied to I, this is equal by definition to alpha applied to beta of I. But since alpha is order decreasing, this is less than or equal to beta of I, the argument. And since beta is order decreasing, this is less than or equal to I. And this shows that the composition of alpha and beta is an order decreasing transformation, so it belongs to Dn. And this means that Dn is a sub-semigroup of Tn. So in fact, Dn is a submonoid because it obviously contains the identity element of Tn, which is also order decreasing. To compute the cardinality of Dn, let us note that if we want to construct an element alpha of Dn, we can do it in the following way. We can choose the value of alpha at the point 1 in one way, because this can only be 1. We can choose alpha of 2 in two different ways, so it can be 1 or 2. And so on. The value of alpha at n can be chosen in n different ways. It can be 1, 2, 3, all the way up to n. And these choices are independent of each other. So we can use the multiplication rule and conclude that the cardinality of Dn is equal to the product 1 times 2 times and so on all the way up to n. That is n factorial. So it remains to describe and enumerate the idempotence of Dn. Let us recall that for an element alpha of the full transformation semigroup Tn, we have defined the kernel of alpha, denoted kappa alpha, as the equivalence relation on our set n underlined, given by the following description: a pair I, j belongs to this equivalent relation if and only if alpha of I is equal to alpha of j. Furthermore, this element alpha in Tn is an idempotent if and only if, for any equivalence class omega of the kernel of alpha, the value of alpha at any element of this equivalence class belongs to this equivalence class. So now we can reformulate our question in the opposite way. If we have an idempotent alpha in Tn, when does this idempotent belong to Dn, to our sub-semigroup? So when is an idempotent alpha from Tn order decreasing? So we take alpha in Tn and we assume that alpha of omega belongs to omega for any equivalence class omega of the kernel of alpha. If we want this alpha to be in Dn, for any equivalence class omega of the kernel of alpha, we need alpha of omega to be the minimum element of omega. Because if this is not satisfied, then the minimum element of omega will go under alpha to something which is strictly bigger than that element. So that alpha cannot be order decreasing. So if we want to ensure that alpha is order decreasing, any equivalence class omega of the kernel of alpha should be mapped to its minimum element. So, and this is if and only if. Given an equivalence relation eta on n underlined, there is a unique idempotent alpha eta in Dn, such that the kernel of this idempotent is eta, and it is defined in the following way. If we have an equivalence class omega of eta, then alpha eta sends all elements of omega to the minimum element of omega. So in other words, there is a bijection between idempotence in Dn and equivalence relations on the set N underlined. So in particular, the number of idempotence in Dn is the number of equivalence relations on our set N underlined, and the number of equivalence relations on a finite set is given by the so-called Bell number Bn. That's a special sequence with the name A000110 in the online encyclopedia of integer sequences. The values of Bn for small n are 1, 2, 5, 15, 52, 203, and so on. Problem 2. Prove that the relations L and H on Dn coincide with the equality relation. Solution. If L is the equality relation, then H, which is defined as a certain subrelation of L, also must be the equality relation. So we only need to prove that L, that the left Green's relation, is the equality relation for Dn. Let us recall that two transformations alpha and beta in Tn are left equivalent if and only if they have the same kernel. So kappa of alpha is equal to kappa of beta. Since Dn is a subsemigroup of the full transformation semigroup, if we have two elements of Dn which are left equivalent, they are also left equivalent as elements of the bigger semigroup Tn. So in particular, they must have the same kernel. So if we have two elements alpha and beta in Dn which are left equivalent, then for sure the kernel of alpha is equal to the kernel of beta. Next, recall that for any transformation gamma in Tn, we have defined the image of gamma as the set of all elements of the form gamma of I, where I is an element of n underlined. So the image of gamma is a subset of n underlined. And the rank of gamma is defined at the cardinality of the image, and that's the same thing as the number of equivalence classes in the kernel of gamma. So now we have two elements alpha and beta in Dn which are left equivalent. So in particular, from our characterization of left equivalence, alpha is equal to gamma after beta for some element gamma in Dn. Let us denote by k and m the maximal elements in the image of alpha and in the image of beta, respectively. Since gamma is an element of Dn, gamma applied to any I gives something which is less than or equal to I, for any I, in particular for any I in the image of beta. So in particular, in order to obtain image of alpha, since alpha is equal to gamma after beta, we take the image of beta and apply gamma, and gamma is order decreasing. So it follows that the maximal element in the image of alpha is less than or equal to the maximal element in the image of beta. By the similar argument applied to the situation when alpha and beta are swapped, we got the opposite inequality, that m should be less than or equal to k, and this implies that k is equal to m. And now we can apply exactly the same argument to the penultimate elements from the point of view of the size in the image of alpha and the image of beta, and proceed inductively. And so using induction, we conclude that the image of alpha must be equal to the image of beta. So we conclude that if we have two left-related elements alpha and beta in Dn, then these two elements have the same image and the same kernel. Now, since the image of alpha is equal to the image of beta, in the equality that alpha is equal to gamma after beta, the element gamma induces a bijection between the image of beta and the image of alpha. Moreover, since each element in gamma is order decreasing, we get that this bijection should be the identity. So the images coincide, gamma induces a bijection and should decrease the order, weakly decrease the order. So this means that gamma must be the identity when restricted to the image of beta. And now if we combine this with the fact that the kernel of alpha and the kernel of beta are the same, we obtain that alpha is equal to beta. And this completes the solution of problem 2. Let us remark that as a part of problem 2, we have shown that the relation H on Dn is trivial, so it coincides with the equality relation. From this it follows that all maximal subgroups in Dn are trivial because they are just H classes containing idempotence. So all maximal subgroups in Dn are singletons. Problem 3. Prove that the relations R, D, and J on Dn coincide. Moreover, two elements alpha and beta in Dn are right-related if and only if the image of alpha is equal to the image of beta, and for any element I in this common image, the minimal elements in the preimage of I under alpha and the preimage of I under beta coincide. Solution. Let us first note that the relations D and J coincide on our semigroup Dn because our semigroup is finite. In any finite semigroup, Green's relations D and J coincide. Furthermore, the relation R coincides with D for our semigroup, since the relation D is the minimal equivalence relation which contains both R and L. And we have just proved in the previous problem that L is the equality relation. So this means that R is equal to D. So it remains to prove our characterization of the right relation in the formulation that two elements are right related if and only if their images are the same, and for any element I in this common image, the minimal elements in the pre-image of I under both alpha and beta coincide. Recall that two elements in Tn are right equivalent if and only if they have the same image. Therefore, if we take alpha and beta in Dn, which are right equivalent, they are also right equivalent in the full transformation semigroup, and hence they have the same image. Also, from our alternative description of the right relation, we can write alpha as beta after gamma for some gamma in our semigroup Dn. So let I be an element in our common image. Let omega be an equivalence class of kappa alpha, such that alpha of omega is equal to I. So this means that omega is the preimage of I under alpha. And let k be the minimal element in omega. Let omega prime be the preimage of I under beta, and let k prime be the minimal element in omega prime. Since I is equal to alpha of k, and alpha is equal to beta after gamma, so alpha of k is equal to beta of gamma of k, we have that gamma of k should belong to omega prime. So in particular, k should be greater than or equal to gamma of k because gamma is an element in Dn, not Tn but Dn. And gamma of k belongs to omega prime, and omega prime has k prime as a minimal element, so gamma of k is greater than or equal to k prime. So this shows that k is greater than or equal to k prime, and if we swap the roles of alpha and beta, we similarly get that k prime is greater than or equal to k. And so k prime should be equal to k. So in other words, we have just proved that for any element I in the common image, if we take the preimage of I under alpha and under beta, then the minimal elements in these two preimages coincide. Conversely, let alpha and beta be two elements in Dn such that they have the same image and satisfy this condition that for any element I in the common image, the minimal elements in the preimages of I under alpha and beta coincide. Take as gamma the unique idempotent in Dn, we know how the idempotents look like, which has as its kernel the kernel of beta. So for any equivalence relation, we have a unique idempotent in Dn. If we take the equivalence class, everything there sends to the minimum element in this class. Take alpha in the common image and let k be the minimal element in the preimage of I under beta. Note that the same k is the minimal element in the preimage of I under alpha by our assumption. Then, for any element s in the preimage of I under beta, we have gamma of s is equal to k by the definition of gamma, and hence alpha after gamma of s, this is equal to alpha of k, which is equal to I, and this is equal to beta of s. And this proves that beta is equal to alpha after gamma. Similarly, if we swap the roles of alpha and beta, we can construct gamma prime, which is the unique idempotent whose kernel is a kernel of alpha, and have that alpha is equal to beta after gamma prime. So from our alternative description of the right relation, we get that alpha is right equivalent to beta. And this completes the proof of our description of the right relations. Two elements in Dn are right related if and only if they have the same image, and for each element in this image, the minimal elements in the preimages of this I under alpha and beta coincide. Problem 4. For a positive integer n, denote by On the set of all elements alpha in the full transformation semigroup Tn, such that for any pair of elements I and j in our set n underlined, which satisfy the condition that I is less than or equal to j, we have that alpha of I is less than or equal to alpha of j. So such elements are called order-preserving transformations, so they preserve the order of elements. Prove that On is a sub-semigroup of Tn, so that's called the semigroup of order-preserving transformations, and determine the cardinality of On. Solution. For two elements alpha and beta in On, and any pair of elements ij in n underlined such that I is less than or equal to j, from the definition of On, we have that beta of I is less than or equal to beta of j, because beta is order preserving. And so alpha after beta applied to I, this is equal to alpha applied to beta of I, but beta of I is less than or equal to beta of j, and alpha is order preserving, so this is less than or equal to alpha applied to beta of j, which is alpha after beta applied to j. And this shows that the composition of alpha after beta is also order-preserving, so belongs to On, which means that On is a sub-semigroup of Tn. Again, On is a submonoid of Tn because the identity is obviously order-preserving. To compute the cardinality of On, note that each element alpha in On is uniquely determined by the sequence of the values of this element at the elements of our 1, 2, and so on n. And this sequence is weakly increasing. So alpha of 1 is greater than or equal to 1, alpha of 2 is greater than or equal to alpha of 1, and so on, all the way up to alpha of n, which is greater than or equal to alpha of n minus 1, and less than or equal to n. Let us define di as a difference between two consecutive elements in this sequence. So di is equal to alpha I plus 1 minus alpha I. So here I is between 0 and n, and by convention we define alpha of 0 as 1 as a starting element, and alpha of n plus 1 as n. So we have n plus 1 differences di, so we have d0, d1, and so on, dn. And then, of course, if we add all the differences, d0 plus d1 and so on plus dn, we get exactly the difference between n and 1, so n minus 1. And of course, by definition, all di's are non-negative integers, because the sequence here is weakly increasing. And of course, d0, d1, and so on, dn determine alpha uniquely. So the number of ways to construct alpha coincides with the number of ways we can solve this equation, d0 plus d1 plus and so on plus dn is equal to n minus 1, and we want to find non-negative integer solutions to this equation. And of course, the total number of non-negative integer solutions to such an equation is equal to a choose b, where a is n minus 1, so the right-hand side, plus n, which is the left-hand side minus 1, so it's 2n minus 1, and n minus 1 is just the right-hand side. So it's 2n minus 1, choose n minus 1. So the cardinality of On is 2n minus 1, choose n minus 1, which is the same as 2n minus 1, choose n. Problem 5. Recall the Fibonacci numbers fi, so f1 is equal to f2 is equal to 1, and fn is equal to fn minus 1 plus fn minus 2 for each n greater than or equal to 3. Prove that the number of idempotents in On equals f to n. Solution. Denote the number of idempotents in On by An, where n is greater than or equal to 1, and set A0 to be equal to 1. Let alpha be an idempotent in On. Since alpha is order-preserving, the kernel of alpha is a consecutive partition of the set N underlined, in the sense that each equivalence class of the kernel of alpha is an interval consisting of consecutive integers. Let omega be the equivalence class of the kernel of alpha, which contains 1. So it starts with 1 necessarily, and then it goes up to some number k, which can be 1 or can be 2, all the way up to n. As alpha is an idempotent, alpha of omega should belong to omega, and this value can be chosen in k different ways, because omega contains k elements. And at the complement of omega, alpha acts as an idempotent order-preserving transformation of the set k plus 1, k plus 2, and so on, all the way up to n. And this implies that our number an, so that's a number of idempotents in On, satisfies the following recursion. An is equal to the sum over all k from 1 to n, k times an minus k. And clearly A1 is equal to 1 and is equal to F2. Therefore, if we want to prove that An is equal to F to n, we only need to check that F to n satisfies exactly the same recursion. So let's derive this kind of recursion for F to n using the Fibonacci recursion. So we start from F to n, and by the Fibonacci recursion, F to n is equal to F to n minus 1 plus F to n minus 2. So we leave this F to n minus 2 and rewrite F to n minus 1 as F to n minus 2 plus F to n minus 3. Now here, we leave this F to n minus 3 and rewrite F to n minus 2 as F to n minus 3 plus F to n minus 4. So we get F to n minus 2 plus 2 F to n minus 3 plus F to n minus 4. Now we look at the second term, and in the second term, we rewrite this as 2 F to n minus 4 plus 2 F to n minus 5, and this as F to n minus 5 plus F to n minus 6. So we get the coefficient 3 at F to n minus 5, and we have F to n minus 6. So now we have what we need, 2 times F to n minus 4, and the new term 3F to n minus 5 plus F to n minus 6. We rewrite it again, and we get 3 times F to n minus 6 plus 4 F to n minus 7 plus F to n minus 8. And now we see that this grows by 1 at each step, and so we have here we have coefficient 1, here we have coefficient 2, here we have coefficient 3, from this step we get coefficient 4, and this continues all the way, and gives us for F to n the recursion that F to n is equal to the sum k from 1 to n, k times F2 times n minus k. So since both the starting values agrees and the two recursions agrees, we deduce that an is equal to F to n. Problem 6. Describe Green's relations and maximal subgroups in On. Solution. Let us start with the left relation L. Let alpha and beta be two elements in On which are left related. Then they are also left related in the full transformation semigroup. In particular, the kernel of alpha is equal to the kernel of beta. Let us try to see whether the fact that the kernel of alpha is equal to the kernel of beta is enough to deduce that alpha and beta are left related in On. So assume that the kernel of alpha is equal to the kernel of beta, and consider the image of alpha and the image of beta. These two sets can be different, but of course they have the same cardinality, the rank of alpha, which is equal to the rank of beta, which is the cardinality of the image, the common cardinality of the image, which is the common cardinality of the number of equivalence classes of the kernel. Let us write image of alpha as the elements I1, I2, and so on ik, so we have k elements which are naturally ordered. And image of beta also consists of k elements, let's say j1, j2, and so on, jk, also naturally ordered. Define an element gamma in On as follows. Gamma sends 1, 2, and so on, all elements up to I1 to J1. Then gamma sends I1 plus 1, I1 plus 2, and so on, all the way up to I2 to the element J2. And so on. And in the remaining segment, gamma sends ik minus 1 plus 1, ik minus 1 plus 2, and then all the way up to n, all these elements are sent to jk. And so by construction, beta is equal to gamma after alpha. And similarly, we construct gamma prime in On such that alpha is equal to gamma prime after beta by swapping the roles of alpha and beta. And this means that alpha is left equivalent to beta to our alternative description of L. Consequently, two elements in On are left equivalent if and only if they have the same kernel. So the description is exactly the same as for the full transformation semigroup. Next, let us move to the right relation R. Let alpha and beta be two elements in On which are right related. Then they are also right related in the full transformation semigroup. Therefore, their images coincide. Now let us try to see whether the fact that they have the same image would be enough to deduce that alpha and beta are right related in On. Assume that the image of alpha is equal to the image of beta, and write this image as I1, I2, and so on ik, so we have k elements which are naturally ordered in the usual order. Note that the kernel of beta is an order consecutive partition of n underlined, because beta is in On. Let us pick some cross-section X of the equivalence classes of the kernel of beta. Note that X has k elements. Define gamma as an element in On, so that's a unique element whose kernel is the kernel of alpha and whose image is X. And then by construction, alpha will be equal to beta after gamma. So gamma sends elements in the kernel of alpha to the cross-section of the elements in the kernel of beta, and then beta sends them to the image, and order is preserved, and the image of beta is the same as the image of alpha. So this gives us alpha is equal to beta after gamma, and similarly we can construct gamma prime such that beta is equal to alpha after gamma prime. Therefore, alpha and beta are right related. So two elements in On are right related if and only if they have the same image. This immediately gives us that two elements in On are H-related if and only if they have the same image and the same kernel, and two elements in On are D-related if and only if they have the same rank. This is a common cardinality for the image or the number of equivalence classes in the kernel. And of course, we already know that D and J coincide in On because it's a finite semigroup. So this gives us a complete description of Green's relations. It remains to comment on maximal subgroups. So these are exactly the H-equivalence classes containing idempotence, but an H-equivalence class is determined uniquely by the common kernel and the image of its elements. And if we fix such kernel and image, this information determines the element of On uniquely because the element in On is order preserving. So the kernel is an order consecutive partition of n underlined, and we take these parts in order and send them in the same order to the elements in the image. There is only one element in On with this datum. So in other words, it means that H-equivalence classes are singletons, and which means that all maximal subgroups in On are trivial, so they consist of one element, just the idempotent. And we already know what the idempotents are. And this completes solution to problem 6. Additional problems and questions. Problem question 1. Show that Cn, defined as the intersection of On and Dn, is a subsemigroup of Tn, and determine its cardinality. So Cn is called the semigroup of all order preserving and order decreasing transformations. Problem question 2. Describe idempotents in Cn and determine their number. Problem question 3. Describe Green's relations in Cn. Problem question 4, describe maximal subgroups of Cn. And problem question 5, describe two-sided ideals in Dn, On, and Cn. Thank you very much and see you next time.